Indeed.
Welcome to the Picture Language Seminar. We're very pleased today to have Yann LeCun. Yann is well known. In fact, I saw on the internet that you're called the Godfather of machine learning. And so we're very happy to have you describe this subject here today. Yann is professor of computer science at the Quran Institute. He's the principal scientist in AI research at Facebook and also vice president of Facebook. And we're very interested to hear what you'll say about the energy-based learning model. So Yann, please share your screen.
All right, thank you, Arthur. I have to say this Godfather denomination is not deserved. You know, I had something to do with something called deep learning, which you'll hear about, but machine learning is older, and I can't claim to anything. And also, even for deep learning, it's a large collection of people who contributed to this. But anyway, so I'm sure this is a very diverse audience. I'm not sure how much you know about machine learning, but I'm going to try to kind of explain some of those things in the possibly in the language of connecting it with the language of physics, and sometimes it's actually inevitable because the mathematics are really similar to what's used in statistical physics, for example, or even classical mechanics, as I'll show in a second. So I'll try to make those connections. Don't hesitate to interrupt me if you have a question. Okay, so the classical way to do machine learning, and what you see, the applications of machine learning you see that you may use without realizing, pretty much all based on something called supervised learning. So you want to build a machine that classifies, let's say, images of cars from images of airplanes. You build a parameterized function. The parameters are those knobs you can adjust. You show an image to the machine. If it produces the answer you want, you don't touch the buttons. And if it doesn't produce what you want, you touch the button so that the answer gets closer to the one you want, okay? Very simple concept, and this works really well. But it requires a lot of data and labeled data that is where the labels, the outputs, the desired output are provided by humans. But that's how virtually every translation, speech recognition, image recognition, driving assistance system, X-ray analysis systems work. You can view this as an optimization problem where the input is the X variable, the desired output is the Y variable. You run X through your parameterized function. It's going to be a neural net of some kind. It makes a prediction, Y tilde or Y bar, and then you measure some sort of distance between those two things or divergence of some kind. And almost all algorithms that work well basically compute the gradient of that cost function with respect to the parameters of the parameterized function. And you take a step in the negative gradient direction. And if you keep doing this, eventually you're going to go down to the minimum. What people actually use is something called stochastic gradient. And what that means is that you don't estimate the gradient of the function over an entire set of training samples. You just estimate it on the basis of either one sample or a small batch of samples and then take a step. And the result of this is that you get a noisy estimation of the gradient, but experimentally it converges much faster than the regular gradient. And so you get this kind of, this is a toy example here where, that shows the trajectory, the convergence here of stochastic gradient in a simple case. Now, what's the idea of deep learning? So deep learning is really why you hear about AI these days. And it's basically a rehash of all the ideas about neural nets, going back to the 1980s, and the roots of that are in the 1950s. And the basic idea of deep learning is that you build your learning machine by stacking, this at the bottom, by stacking multiple stages of parameterized nonlinear functions. There's no point stacking linear functions because the product of, the composition of linear function is still linear, but if you have nonlinearities in each of those things, then stacking actually gives you some representational power. It took until the 1980s for people to figure out that you can actually compute the gradient of a system of this type. So the gradient of some objective function with respect to each of the parameters of each of the boxes by using a method that is now called backpropagation, but it's basically a practical application of chain rule. In fact, I'm going to go directly to this, right? So imagine you have a function which is a composition of a whole bunch of functional blocks that you apply sequentially. you can just write a chain rule, the gradient of the loss function with respect to a particular vector inside the state vector here between two blocks inside of this machine. But just writing chain rule is the gradient of that function with respect to the state at the next stage, multiplied by the Jacobian matrix of that box with respect to its input. And what that suggests is that you can have kind of a recursive algorithm that sort of goes back those green arrows here by multiplying these green vectors with the Jacobian of each box successively. You can compute all the gradients of this loss function with respect to everything in your network. You have a similar formula when you have internal parameters for those for those modules. So that's the backpropagation algorithm. It's a chain rule, nothing more. But it took until about the 1980s, the mid 1980s, if not the late 1980s, for people to figure out that you could use this for machine learning. In fact, now it's more generalized. It's called differentiable programming. You can actually write a program in Python or your preferred language, and it gets automatically differentiated. And there's been methods to do this going back many years, but it's become kind of a standard tool now because of deep learning. So now the next question is what do you put in those boxes? And there's a lot of work in convolutional nets and things like this, which I'm not going to go into. There's a lot of interesting work, applications of this to physics that have appeared in the last few years. This is just an example of work from the Flatiron Institute in New York of this team that used a particular type of architecture called UNet, which is sort of a form of convolutional net, to basically accelerate the solving of essentially what comes down to a partial differential equation for computing cosmological quantities of various kinds. And it makes the computation so much faster that you can basically simulate the early instance of the universe. This was a PNAS paper a couple of years ago. There's a lot of use of this, including at Harvard. Actually, these are some of your colleagues at Harvard on high energy physics and things like that. But here is an interesting connection with classical mechanics. You can derive backpropagation as basically as if it were a Lagrangian problem, which really is directly lifted out of classical mechanics. So you have a loss function, which is something that measures the discrepancy between the output you want and the output you get at the output of that chain of functions. But you have a constraint to satisfy, which is that the input to block number k plus 1 must be equal to the output of block number k. And then the z0 is equal to the input, right? So you can write this as a Lagrangian. Here's the Lagrangian, this function of all kinds of variables. That's the cost you want to optimize, and that's the set of constraints. Zk plus 1 equal gk, of zk wk. So input of stage k plus 1 equal output of stage k multiplied by Lagrange multiplier, which is a vector because this is a vector. And then you write the optimality conditions. So dl over d lambda, you just get the forward propagation formula, which is nothing new. And then dl over dzk, you get this interesting formula here that if you rewrite it, basically tells you this is backpropagation. That's the backpropagation formula. The gradient at stage k minus 1 is equal to the gradient at stage k multiplied by the Jacobian of the functional block that relates lambda k minus 1 to lambda k. So, just like 3 lines of calculus and you get backprop, okay? And it's just classical mechanics, nothing more. Lagrange could have figured this out. In fact, he did. But then how are you going to use this for machine learning? That's the question. So easy to understand. Now let me talk about the problems that people are interested in machine learning and AI these days. And one problem is supervised learning is nice, but it requires many samples for the system to actually learn. So you have to hire people to label images and to transcribe speech, to translate speech in one language to text in one language to text in another language before you can train a system in supervised mode. And there's a lot of problems for which it's either impossible or economically impractical to basically go through this. For example, you want to translate one rare language into another rare language. You're not going to have parallel text between those two languages. So there is a push to find techniques that allow machines to learn with fewer label samples. basically learn to represent the data without being trained for a particular task, okay? And that's the idea of self-supervised learning. There's also learning to reason, which I'm not going to talk about very much, and learning to plan complex action sequences, which I'm not going to talk about either. Okay, so first question is, how is it that humans and animals seem to learn so quickly and learn so many things about the world, right? Your house cat has incredibly good intuitive physics model. You know, a house cat has about, I think, 870 million neurons compared to 86 billion for humans. Yet in terms of, you know, the sort of dynamical model of their own body, it's incredible. How do they learn that? They don't learn this in supervised mode, certainly. And in fact, baby humans learn very few things supervised. Most of the stuff that we learn as humans, we learn as babies. And we learn very basic things like the world is three-dimensional. Why is the world three-dimensional? It's because to explain how my view of the world changes when I move my head, the best explanation is that every point in the world has a distance from me. And you know, it explains sort of parallax motion. It's not clear whether that is innate in the human brain or whether it's learned. It's probably learned. Things like object permanence, the fact that when an object is hidden behind another one, is still there. You may not see it, but it's still there, right? Babies learn this, you know, by the age of 2 months or so. And then things like, you know, intuitive physics, like gravity, the fact that an object is not supported will fall, inertia, conservation of momentum, things like that. They become kind of you know, part of your model of the world by the age of 9 months or so. Before the age of 9 months, you show this little scenario here on the left to a baby, like a 6-month-old baby, and baby will, you know, not pay attention to it, basically not be surprised at all. But a 9-month baby has figured out that objects that are not supported are supposed to fall, and they'll make a face like the little girl here on the right. So how is it that, you know, we learn models of the world by observation? We are extremely good intuitive physicists, and so are many animals. We can't do this with machines today, okay? And that's probably where we learn our background knowledge. That's probably the basis of common sense, is this kind of learning all the thing about the world by observation, okay? What we learn through supervised learning at school or through our parents, what we learn by reading books is kind of a tiny sliver of knowledge. We think it's like, it's everything, but it's actually a small sliver. The most complex thing to learn is things like vision and, you know, motion, intuitive physics, predicting how people behave, things like that. In fact, this idea that common sense is not facts, but a collection of models actually goes back to classic work in physics, in psychology many years ago. Okay, so what is this self-supervised learning? What would be a hypothesis about what self-supervised learning is? It would be basically learning by prediction, learning to fill in the blanks. So if I show you a small video clip and I ask you to predict what's going to happen next, you can have a good guess as to what's going to happen next. Here, there's not much happening. The little girl is going to blow on the candle, but you know, you have a segment of video. I show you a segment of video. I ask you to predict the remainder of that video, or maybe I show you a few frames and I ask you to fill in what's missing, or maybe I only show you the left part of a video frame and ask you to predict the right part, or something like that, right? So self-supervised learning is filling in the blanks. You have a partial view of a piece of data. Eventually, you see the full thing, and so you can correct your model of the world to kind of predict what was actually observed. And that can be used for two things. It can be used for training models to represent, to run representations of the world in an unsupervised fashion. Okay, so you just have a system watch videos all day, and by the end, it's figured out there are objects in the world that can move independently of others, and there is, you know, most objects follow a predictable trajectory, except, you know, animate objects and things like that. I'm talking about something that does not exist yet. Okay, people are working on it, but it doesn't work yet. But that would be one use. And then the second use would be learning predictive models of the world that would allow us to essentially predict in advance what's going to happen in the world and then use it to plan ahead. But the big question here is, and we were just talking about this with Dan, is how do we represent uncertainty and multimodality in the prediction? And that's where energy-based models come in. And again, a lot of the math here is inspired by statistical physics, essentially. Okay, so when we do video prediction, there is a lot of different things that can happen in a video following an initial segment. Okay, you're watching me right now. I could be moving my hand this way. I could be kind of, turning my head this way or that way. I could be saying a different word than the word I'm just saying. You cannot completely exactly predict what's going to happen to me. And if I ask you to make one prediction that minimizes the prediction error, the best thing you can do is predict a blurry version of me, which is the average of all the possible things I could do, okay? And that's a bad prediction. But it would be the prediction that minimizes the squared error between, between your prediction and all the things that could possibly happen. So if you ask a system to make a single prediction, you don't get, in a situation where there are multiple compatible y's with a given x, you just get a blurry mess, okay? Now, what we're going to do is we're going to replace this by an implicit function, an energy function. We're going to call it an energy function, f of xy. And the role of this energy function is to measure the compatibility between x and y. Okay, so if I give you a video clip x and another video clip y, if y is good continuation for x, f of xy would be low energy. And if y is not a good continuation for x, f of xy would be large, high energy. Okay, so f of xy measures the incompatibility between x and y, essentially. And the inference process, so I'm not talking about learning yet, but the inference process, if you really want to make a prediction for y, would consist in, given an x, finding a y, there might be multiple y's, that minimize this energy function. Okay, so inference basically comes down to minimizing an energy function. Okay, we haven't talked about learning yet. Okay, this energy function is just used for inference, for prediction, if you want. There are multiple energy functions that will give you the same prediction. Here's an example where x is a scalar variable, y is a scalar variable. The dependency between y and x is that y equals x squared or something like that. And those two energy functions give you the same y for a given x with, the same y has the lowest energy for a given x. So if your energy function is discrete, is continuous and differentiable, you can do inference by gradient descent or something like that. Otherwise it might be more complicated. And there are two forms really of those energy-based models: the conditional ones, where you have an x that you observe and you predict, you model y. But there are another form called unconditional, where you only have a y, you don't have an x. And for a particular situation, you may observe a subset of y, but you never know in advance which subset you're going to observe. So for example, imagine that you are a situation where I show you an image, but a part of the image is blocked by an object, and you would like to remove this object and infer what's behind it. But you never know, in two cases where this occluding object will be. And so you never know which part of y will be observed, which part will not be observed. So x is what is observed all the time. Y is what is either observed or not observed, but you never know which until you're shown. Now, of course, Gibbs and Boltzmann figured out a long time ago that you can turn energy functions into distributions, to probability distributions with maximum entropy using the Gibbs formula. And so if you're really interested in getting a distribution over y given x, you can take e to the minus f of xy, which is the energy of this pair xy, and then normalize by the integral over y of that energy. That's the partition function, and you get a nice normalized distribution, a conditional distribution of y given x. So that's if you want to kind of turn an energy-based model into a probabilistic model. But it turns out, as many of you I'm sure are well aware, this thing at the bottom here tends to be intractable in many cases. I'll come back to this in a second. So let me talk now about architectures of energy-based models. There are two types of architectures, really. The first one, which is really popular in image recognition over the last year or so, is called joint embedding architecture. So joint embedding, it's a way of handling the multimodality of y by basically running y through a neural net. So let's think about a situation where we feed, let's say, a video clip to x. We run it through a neural net, parameterized function of some kind. It gives us an output vector here, h. And then we run another video clip, which may or may not be compatible with x, through another predictor. And it produces a representation. Then we compare those two representations. If they are similar according to some distance, C of h prime, it's low energy. If they are dissimilar, it's high energy, right? So the energy function is the similarity between h and h prime. Now, this can represent multimodal predictions of y given a single x, because this predictor may have an invariant subspace. So there may be a whole collection of y's that leave h prime unchanged. And what that means is that all of those y's will have exactly the same energy for a given x. Okay, so one way to represent uncertainty is by running y through a function that has an invariant subspace or invariant manifolds or whatever. And that we give a whole, manifold of y that all have the same energy. So that's one way of handling multimodality. Now, it's not at all clear that you can turn this energy model into a probabilistic model, because it's quite possible that the partition function, when you kind of infer the energy of for all y, does not converge. Okay, you will have to regularize it of some kind. So this is an energy-based model that may not have a probabilistic interpretation. And that's the whole idea of energy-based models. Okay, you basically do away with probability theory, replace it by something a little weaker, but maybe less intractable. That's the second type of architecture for energy-based models, and it would be that can handle multimodal prediction, and it's latent variable predictive or generative models. So here, the way you allow the system to represent a whole manifold of possibilities for the prediction is that you have a latent variable that can vary over a set that you predetermine. And as you vary this latent variable over a set, the output, the prediction, varies over a set, a manifold, let's say. Okay. You may have a distribution of this latent variable, which will actually produce an implied distribution over this set. And those are the only two architectures I know, okay, to represent multimodal outputs. Joint embedding, exploit invariance, or latent variable models. Let me skip this. Okay, now, if you have a latent variable model, you can turn it into a non-latent variable model with a trick that physicists invented a long time ago, or actually probability theory people, statisticians invented a long time ago, called marginalization. So what I can do, or energy minimization. So here I have a latent variable model that depends on x and y, and as well as a latent variable z. I can do inference by minimizing this function with respect to y and z, and then I get a y that has low energy and simultaneously with a z that has low energy. I can turn this energy E that has a z inside of it into an f by basically minimizing with respect to z. And that's, you could call this a free energy, which is why I call it f. But that's a limit case, zero temperature limit, in fact, of a slightly more general case where the free energy f of xy is now defined as -1 over beta, where beta is an inverse temperature, log integral over z of e to the minus beta e of xyz. This is the log partition function where the integral goes over z. And that's the Helmholtz free energy, basically. And now what we've done here is basically turn a latent variable energy-based model into a regular energy-based model that doesn't have a latent variable through this integration. This may be intractable again, so we may have to do things like variational approximation. This is boring math that I'm not going to show you. Okay, how do you train an energy-based model? There are two classes of methods. The older one is contrastive methods. So contrastive methods consist in picking a data point, which is one of those blue dots here. You take a data point and you change the parameters of the energy function, which inside of it has neural nets. Okay, so you change the weights of those neural nets so that the energy goes down. Okay, and that's kind of the classical thing that basically every machine learning system does. Minimize the error between the prediction and the thing you observe. That's what you do. But in an energy-based model, you have to have another thing that guarantees that the energy of other values of y for a given x are higher than the one you just trained on. Or not just one, you might have multiple y's that you trained on, and you want all of those y's to have lower energy than all the other ones. So you might need to push up the energy of other points. And that's where things become complicated. So you have to pick a point y hat whose energy you're going to push up. And when I say 1 point, it could be multiple points. So that's the idea of contrastive methods. And pretty much all probabilistic methods are contrastive in some ways, at least the powerful ones. And then there is another approach, which is regularized or architectural methods. And in there, you build f of xy so that the volume of low energy region is limited or minimized through a regularization term. And so if you have some term that becomes large, if the volume occupied by low energy points becomes too large, then the system will try to kind of minimize, we basically kind of try to shrink wrap the data points that you train to have low energy. It will automatically give high energy to any point outside because you're minimizing the volume of stuff that can take low energy. Okay, this is much more efficient, but it's a little finicky. So I'll come to examples of how you do this. So here is an example of contrastive loss. You take the energy of a data point, a blue dot here, so blue y, and you take the energy of another point, a contrastive point, y hat, which is one of those green dots. You plug this into, so you compute the difference between the two, add what's called a margin, and you plug this into the positive part. So this is a half-wave rectifier that is 0 if the argument is negative, and the identity function if the argument is positive. And when you minimize this function, it's going to want to make the energy of the blue point, the blue dot, lower than the energy of the green dot by at least this margin, okay, which you can set by hand or something. So that's an example of contrastive method. Here is an example of regularized method. So you use this regularized latent-variable model, and you put a regularizer on Z that says, you know, I don't want Z to have too many non-zero components, for example, right? Sparsity. And that turns out to kind of limit the volume of stuff that can take low energy. Or you make Z discrete. So then there is only a finite number of points in the space of Y's that can have 0 energy, essentially. So I don't expect you to read all of this, but I tried to make a catalog of all the classical methods that people have used in machine learning to train models as to whether they are contrastive or regularized or architectural. And I'm not going to go through this list. I'm just going to point out a few things. Before that, you can train an energy-based model with maximum likelihood. So the likelihood of a y given an x, according to the Gibbs-Boltzmann distribution, is this expression. And what you might want to do to train your system is do maximum likelihood, or more practically, negative log likelihood. So you take the negative log of this probability for all of your data training points, x and y, and that's the negative log of this ratio here. I divided by beta, so I wouldn't have to carry this thing. And so this loss function says make the energy of a data point low, and then push up on the energy of all data points, I mean all points in your space, including the correct one. This term is a decreasing function of the energies of all the points. And so when you compute the gradient, it's going to push up on it. In fact, when you compute the gradient of this with respect to, let's say, the parameters of the energy function, you get this expression. So this says there's a force on the energy of the data point that pushes down. And here there is a force on the energy of all the points that pushes up in proportion to the probability that your model gives to that point. Okay, so if your model gives a high probability to the point, it means it has low energy, it gets pushed up really hard. Those two things balance once the energy of your data point is infinitely smaller than the energy of the other points. Okay, and that's bad. It's bad because it leads to energy surfaces that basically look like canyons. And that means you can't do inference with this. And so I have the hardest time convincing my colleagues in the machine learning community that they should abandon maximum likelihood and probability theory in favor of energy-based models with other objective functions, because probabilistic modeling leads to bad solutions. Okay, this sounds completely kind of unorthodox, and it seems to kind of, you know, break every textbook you've read, but it's true. So, you know, you can use all kinds of different objective functions, which I'm not going to go through. There's a whole catalog of them that people have used over the years for various purposes, not formulated in the context of those things, but they all have the same type of property that, you know, you can view them as basically trying to shape an energy function that gives low energies to good things that you train it on and high energy to other things, essentially. I'm going to skip this. Okay, so here is an example of interpretation of a very successful recent advance in machine learning in terms of energy-based model, and it's called Mast autoencoders. Okay, so what is a Mast autoencoder? Let's say you want to train a system to represent text, learn a representation of text. You don't want to train it for a particular task of text classification or translation. Just you want to train it to represent text in the form of numerical sequence, like vectors or sequence of vectors. So the method that has become completely standard these days is you take a text, you run, so each word is basically immediately turned into a vector through a lookup table that is trainable. You can think of it as a big matrix, but it's basically the first layer of the neural net. But what you do with this sentence is that you remove some of the words, you replace them by a blank marker, or you substitute by another word. So that's a corruption process. So you get one of those y hats here by corrupting the original y. So think of y as one of those blue dots here in this diagram on the top right, and think of y hat as one of those brown dots. Okay. And what we're going to do is that we're going to train a big neural net to recover the missing words. Okay, so to recover y. So we're going to train it to minimize this basically reconstruction error. Okay. And the result of this is that now when you show this neural net a complete sentence, the complete sentence would be reconstructed as itself. Okay, which means, so if you make no corruption, which means the energy, the reconstruction error, would be 0. Okay, so the blue dots are going to have 0 energy if your system is properly trained. Whereas all the brown dots that you trained it on are going to have an energy equal to the distance between the brown dot and the blue dot it was corrupted from. Okay, because the brown dot here is going to be reconstructed as its blue dot. And so the reconstruction error of a brown dot that you feed here is going to be the distance between the brown dot and the blue dot. Okay, so that's going to lead to an energy surface that looks like this at the bottom here, where you have kind of a groove in the energy profile around the manifold of data, and the energy goes up around, and there is kind of a bad side effect here in the center where the energy is low in the middle. So it's a kind of phantom spurious minimum in the energy that pops up because of the way you built it. Now, this works amazingly well in natural language processing. Every high performance natural language processing system that is used today, deployed, by Facebook, Google, Microsoft, IBM, everybody, is pre-trained this way. Okay, you train with billions of pieces of text, and it works amazingly well. In fact, it even works for doing, solving math problems, right? You generate a bunch of formulas, you differentiate those functions, and now what you have is a training set of functions and their integral. Okay, and you train one of those giant systems to basically predict a representation of the formula of the integral given an expression. And it works. And it works better than MATLAB and Maple and Mathematica, which is kind of amazing. It even works for simple first order and second order differential equations, not PDEs, okay? Just ODEs for now. This is amazing. It's totally amazing. And there's some more work there that this team is doing. But this doesn't work for images. So if you use the same idea, you take an image, you block some pieces of it, you train one of those things to kind of recover the missing parts, and then you try to figure out, like, can I use this representation internally to, as input to a image classifier? It doesn't work very well. And it's because those systems don't represent the uncertainty, the multimodality in the prediction. It's easy to do for text because you can have a probability distribution over words, but not on images. So here is what works for images. What works is what works well is those joint embedding methods. The contrastive method that I explained earlier, you show a pair of images that are identical because you took an image and you transformed it into 2 different ways. You changed the cropping or the orientation, the scale, you changed the colors a little bit. So those 2 images have essentially the same semantic content. You show them to the machine and you tell the system produce the same representation for those 2 images because they're really the same image. And then the contrastive phase is you show two images that are different and that you know are different, and you push those two vectors away from each other, okay, using a loss function that you picked, maybe one of those contrastive loss functions. This works well, but it's very expensive. And the reason is that in a high dimensional space, there are, which is the dimension of those H, there are many, many ways two vectors can be different. And you need to push up on every possible orientation, and it's ridiculously expensive. So that's kind of the learning procedure. There's those names that people give to kind of more or less standard benchmark architectures. This is a convolutional net called ResNet 50. Particular architecture is kind of the workhorse of image recognition, if you want. You get a vector on the output here, which typically is dimension 2000. Then you run it through a couple layers of another neural net. You reduce the dimension, and then it's in this space that you do this contrastive learning, make the representation, those 256 representation, identical for semantically similar images and different for different images. Then what you do is you use those 2000 dimensional representations and feed them to a linear classifier, just a single layer neural net, and you train this as a classifier and you measure the performance. Okay, that's kind of a standard protocol if you want. And it's really expensive computationally. It works okay. It works really well in speech recognition. It's allowed my colleagues at Facebook to essentially train a speech recognition system. So you pre-train it in self-supervised mode using a technique similar to what I just described on something like 1,000 hours of unlabeled speech, okay, which is easy to collect. And then you train a classifier with only 10 minutes of labeled speech, and you get a system that basically has the same performance as a previous system that was trained on 100 hours of labeled speech. That's really important because now what that means is that you can have multilingual speech recognition systems that can basically work with very rare languages for which we barely have any data. So that gives kind of computer access to populations that normally would not have access to it. So it works really well and with multiple languages and everything. Okay, but the hot stuff now, the thing all the cool kids are working on is non-contrastive energy-based training. And that uses this idea of regularizing the volume of space that can take low energy. So in the context of joint embedding methods, I talked about the contrastive approach, which is on the left, and then there's all those approaches here, which have different names: distillation, quantization, or information maximization. I'm not going to talk much about those. They work pretty well. In fact, the best method today are based on quantization. The basic idea, so there's two methods. They came out of Facebook AI research in Paris. One called Deep Cluster and another one called Suave from the same team. And that's based on the idea of essentially taking the vectors that come out of one branch. So in all of those methods, the two branches are identical. They share the same parameters. And it's an essential characteristic of those methods. So here what you do is you run a sample through one of the branches, and then you do a clustering, which is basically a discretization. You say the vectors that come out, they belong to a number of categories. I'm going to decide what those categories are by just running a clustering algorithm. And then I'm going to use the target vector coming out of this clustering algorithm the vectors coming out of this clustering algorithm as targets for the left half. And if you do this properly, it prevents the collapse. So the main issue, the reason why you need this contrastive phase in contrastive learning is to prevent collapse. The collapse is a phenomenon that if you only showed positive samples here, only X and Y's that are, compatible images, the system will happily completely ignore the inputs and produce constant vectors on the output, okay? And that corresponds to an energy-based model whose energy is completely flat, equal to 0 everywhere. Okay, so that's why you have this contrastive phase with contrastive samples that push up the energy of points that are outside, okay? And what we're trying to do now is make sure the energy is high outside of positive samples with another method than pushing up on samples by basically tricks, okay? So this clustering method actually turns out to prevent collapse, but we don't quite understand why. Distillation is even more mysterious. There's a method called BYOL that was proposed by DeepMind a little over a year ago, and they could not explain why it worked. It worked, but they could not explain why. There's been a bunch of theoretical papers that try to explain why it works. The stuff I'm going to focus on is based on information maximization. And this is 2 recent papers coming out of my group at Facebook that basically prevent the collapse by attempting to maximize the information content or information capacity of the vectors that come out of those 2 networks. So let me skip this in the interest of time. So this is an experiment with the Suave clustering technique that my colleagues at Facebook did, where they trained a very large neural net with in self-supervised mode with 1 billion images randomly picked from Instagram. And then they fine-tuned it for in supervised mode on ImageNet, which is kind of a standard data set for measuring the performance of computer vision system. And they got really good performance, something like 84% correct, where a pure supervised approach would produce a little more than 81% correct. So, that tells you the power of those self-supervised approach. So here is the idea of energy maximization here. And this is the Barlow twin idea. Barlow was a computational neuroscientist who proposed the idea that of sort of efficient representation and redundancy minimization. So the way this works is you train the system to produce essentially the same output on both sides, but you also have a criterion that attempts to maintain the variance of each of the components of this vector, and simultaneously try to decorrelate the components of the vectors. Because the system could cheat by basically producing the same value in all the components of the vector that will maximize the variance, but it will not actually give you any useful information. So in addition to this, you minimize the correlation, essentially, between pairs of variables, and that sort of maintains the information content of the variables. And this prevents collapse, and it works really well. There's a second version of this called VICREG, V-I-C-R-E-G. That means variance, invariance, covariance, regularization. I don't actually have it on this slides because it just came out last week from my group, and I neglected to put it in the slides. So this works, in the sort of leading pack of all the self-supervised learning methods for image recognition, which is cool. Let me skip ahead a little bit because I'd like to keep some time for question, and I just want to jump to a few conclusions. I'm just going to flash this. This is, so there are methods that people use in the context of self-supervised learning, a particular method called Variational Autoencoder. And it uses the trick that a lot of statistical physicists use, which is to bound the log partition function by a variational approximation of the free energy using the Jensen's inequality, which allows you to flip the log and the integral and substitute the actual posterior distribution with sort of a substitute one. Anyway, I'm not going to go into the details of this, but this is just to tell you that there is a really deep connection between the mathematics that is used in this context and in fact, and statistical physics. In fact, the author of Variational Autoencoder, one of the authors, the senior author, is Max Welling, and he's actually he did a PhD in theoretical physics with 't Hooft in the Netherlands. But anyway, I don't have time for that. So let me just jump to a few conclusions. Okay, so self-supervised learning is the future of machine learning, in my opinion, and certainly representation learning. Probably non-contrastive methods are really where the future lies. I didn't have time to talk about this, but self-supervised learning can be used as a way to learn predictive world models that would allow machines to reason and plan ahead. This is something I'm really interested in. People have tried to use things like variational autoencoders for that. One big question I'm asking myself, which is why I'm so interested in self-supervised learning, is could a form of self-supervised learning by which machines would be trained to understand the world by just watching video, could this be the basis of common sense for machine? Machine common sense has been sort of a red herring for the last 60 years of AI, and it seems to me that humans acquire common sense because of by acquiring a collection of models of the world, which basically occupy the entire front half of our brains, the prefrontal cortex. You hear someone, you hear sometimes in the press or even the technical discussions about AGI, artificial general intelligence, I do not believe in this concept of general intelligence, because human intelligence is actually very specialized. We'd like to think of ourselves as having general intelligence. We don't. We are super specialized. And in fact, the fact that computers can do a lot of tasks much better than we can shows that we are specialized. There's an interesting conundrum about deep learning these days, which is that to some extent, it's very much an empirical science. Some would say actually it's more like alchemy. Okay, there's a lot of people who try different things and they stumble on something that works. And you know, in physics or natural science, it's a perfectly fine strategy for progress. But you know, with people who have a background in mathematics or kind of more or theoretical computer science, it's not very satisfying. They like nice theory, and deep learning is so messy that it's very hard to do good theory. So I think deep learning is a bit in this situation that a lot of areas of science and engineering were, where you know, we've invented artifacts, but the general theory for it is still to be done. And if you, I made this chart that may or may not be quite accurate, you know, some of you may correct me, but you know, the telescope was invented in 1608 roughly, but you know, the sort of general laws of optics weren't figured out until 50 years later by Newton and others. You know, there were work before that, but that's really where it became formalized. Steam engine, I think, is a better example. So that was invented around 1700, but thermodynamics was really not figured out until over 100 years later. And thermodynamics was really designed to explain the limitations of thermal engines, basically, you know, Carnot cycle and entropy and all that stuff, right? You know, the impossibility of you know, perpetual motion and things like that, second law of thermodynamics. And what's interesting is that, you know, from an attempt to theoretically explain the limitation of an engineering artifact, people came up with thermodynamics, which is the basis of all of modern science, basically, right? And not just physics. So, and you can make a list of a lot of other things like that, where you had the engineering artifact before you had the theory that really kind of explains it. So, so we are in a bit of this phase where people are kind of attempting to make that transition from you know, engineering to theoretical science, and this is what you guys are interested in, I suppose. Okay, I'll stop here. Thank you very much for your attention.
Well, thank you very much, Yann, for a very inspiring talk. And I'm sure that there's a great deal of discussion. In fact, you answered my first question right at the end of your talk, saying that we need a theory. And it would be very interesting to know how to develop that theory. But maybe I start off the discussion by saying that people who contribute should turn on their video so we can see you and actually have a back and forth question and answer. And for the first question, let me ask, you talked about probability theory throughout your talk. You talked about states and you replaced it by weights, and you developed this in many interesting ways. But I wondered if you ever use quantum in the sense of non-commutative variables, which are so important in physics, as well as the classical theory that you've talked about up to now.
Yeah, absolutely. So, I mean, it's something that I'm really interested in. So let me tell you where I come from. You know, back in the early 90s, I was, Yoshua Benjo and I were working together at Bell Labs, and we had this idea that we could essentially build what's called a recurrent neural net, right? So it's a neural net that you take, you have a state vector, you apply a function to it, you get a new state vector, and you keep applying the same function recursively, and that's called recurrent net, right? And you can unfold it in time, and you can train it through backpropagation by backpropagating through time. There's a problem with those networks that Yoshua identified in his PhD thesis, which is that if the function that you applied at every time step is degenerate, then the system will converge to a fixed point. There might be multiple fixed points, but what that means is that because this fixed point is stable, when you backpropagate gradients, you get zero gradient, because you can perturb the initial state a little bit, and the end state will always be the same. So when you backpropagate the gradient, you get 0. And so that's an issue. Like one question we ask ourselves is how do you prevent a recurrent net from having this gradient collapse, so-called vanishing gradient issue. And one idea that I proposed was you make the transformation here orthogonal or unitary, or at least invertible. Okay, so unitary told us, well, why don't we make those vectors complex vectors, and then we apply a unitary matrix and get another complex vector. And of course, that's quantum mechanics. Okay, I mean that's that's how you. I mean the underlying mathematics of quantum mechanics really is that. And we figured we could use this for. We were just talking about this with Dan earlier. You could use this for kind of a new form of probabilistic models, where instead of having a list of states with a probability distributions on them and then multiplying them by, say, a stochastic matrix to get a new distribution over a state, you could use, basically what amounts to amplitude vectors and then unitary transforms. So that would be like a quantum sort of Markov model, if you want. We never actually published it because we couldn't make it work. We programmed it, we tried to make it work, and there was something wrong with it or something. We couldn't figure out how to make it work. And so we abandoned the idea. And then the idea was kind of revived by other people because quantum computing kind of became a thing. And so we said, like, that basically a quantum computer is basically that kind of process. And there's been quite a bit of work on this. I had a couple of papers on this idea of using invertible matrices for a recurrent neural net. I was just last week, actually, I was talking with Seth Lloyd at MIT, who's actually working on this kind of stuff as well, on basically unitary, maintaining the sort of unitarity of a transform that you can apply multiple times. So yes, I'm a big fan of this idea. I'd like to, I'd like to believe perhaps that by going to complex amplitudes and path integrals instead of probabilities, exponentials of energies and integrals, regular integrals, that maybe some of the computational interactabilities will disappear. But I don't think that's true. Unfortunately, I don't think it would solve our problem. Sorry for the long-winded response.
Well, thank you. Maybe there's some other people who have questions or like to make some comment.
Yeah, can I? So you
yourself.
So with this masked autoencoder, you showed that the minimizer for energy is a kind of connected manifold. Is it possible to demonstrate that's actually connected manifold, or is it actually connected in practice?
Well, so there's been quite a lot of work. So I didn't talk about this in this talk because the time was limited, but there is a lot of work, very interesting work, mostly done by people with a background in condensed matter physics, of trying to analyze the landscape of the loss functions in neural nets. And neural nets that work well tend to be over-parameterized. So they tend to be larger than necessary to capture the training set. And what that means is that the minima are very degenerate. There is, every minimum is surrounded by lots of dimensions in which the loss is basically flat. And what's more is that there's some evidence that the different minima are basically linked by a flat area. You can go from one minimum to another without ever having to go up an energy barrier in very sort of overly parameterized neural nets, which are the ones that work best.
So what does it mean for the? Oh, sorry.
Well, there's no proof of this. Okay, there is sort of some empirical evidence, but there's some theory based on kind of various tools from statistical mechanics that kind of show this. There's some analogy with the like locking balls or whatever from Mathieu Viard at EPFL. There's all kind of methods that attempt to kind of show that it's more or less a necessity that you're going to have a lot of saddle points in this energy landscape. You're going to have local minima, but they're pretty high in energy. They're rare, and you have essentially no chance of getting trapped in them.
But so what does it mean in terms of text representation? Because text is something very special. It's designed to convey information. So in a sense, sentences are very constrained and unique. And here we have a whole manifold of parameters that represent the same thing. So what does it mean?
Well, I mean, there are two things, right? There is the vector representation inside, and there is the landscape I'm describing is a landscape in parameter space, right? In the parameters of the neural net. And those are two different spaces, right? There is the space of states, which is also continuous. Okay? So text is being represented by vectors, patterns of activity of simulated neurons or whatever you want to call them, which is very different from the sort of intuitive representation of text and thought that we have, which is basically discrete symbols, right? In fact, there is kind of a bit of a conflict between two views of AI. One that is sort of the classical AI, if you want, that use AI as high-level reasoning and logic based on symbols and etc. And then the sort of deep learning neural net type people who say, well, no, actually, a piece of information is represented by a pattern of activity on a bunch of neurons and perhaps even an orbit or something like that. It's continuous. And the question is, how do you have the emergence of discrete symbols out of continuous representations? The answer to this might be, a multimodal energy landscape, right? So you have if you have an energy, and this idea goes back to Hopfield, in the 1980s, that like a memory in the brain might be the fixed point of dynamics that correspond to kind of the minimum of a Lyapunov function, an energy function. Similar to what you observe in spin glasses and stuff like that. So you go from continuous to discrete by energy minimization. You have discrete minima, and each of those is a discrete concept.
Well, I see that, Klaus, you have you're unmuted. Did you have a comment?
Well, I have a question. Do you think that the future theory of brain is by deep neural networks, where you just look into statistical approximations and don't understand really how they work together?
Well, there is no opposition between deep neural networks and statistical models, right? Deep neural network are a particular type of statistical model. You can think of it this way. Now there's the broader question, is a concept like deep learning, will this be part of future AI systems as we approach AI systems that match human level intelligence? My answer to this is yes. I basically have little doubt that whatever AI system we devise in the future will have as a basic concept or a component this idea of having an objective function you minimize through a gradient-based method. And that's really what neural nets are about, what deep learning is about, right? It's gradient-based optimization algorithm applied to complex structures. Now, that doesn't mean we've solved the problem. The question is, what objective function are you minimizing? What architecture do you give to your system? What principle of learning do you base it on? Do you use those contrastive methods or not? Whatever. How do you do self-supervised learning in a task-independent way? If the system is a robot that needs to explore its world to learn things, how do you deal with this exploration-exploitation dilemma? Do you keep doing the thing that is safe, or are you going to try a new strategy to see what if it could be better? So these are questions that a lot of people in machine learning are struggling with in simple cases. But I think this whole idea of deep learning is going to be with us. Yes. As we go. Now, today, the best models that explain how the visual cortex does vision are basically convolutional nets. Okay, so yes. Neuroscientists use convolutional nets as a model of the visual cortex.
Can you trace a step towards consciousness?
Well, okay, so nobody knows what consciousness is. I actually have a slide on this, which I didn't show towards the end. So consciousness, it's not clear. There are theories of consciousness that I like there's a theory that says, I was talking about those models of the world that we have in our head, right? So you're facing a situation, that you need to, you're in a room and, you need to get out of the room. And, it's, you need to remember where the door is, or maybe look for the door and then walk towards the door. You need to plan your path, avoiding obstacles, stuff like that. It's not very complicated. But you have a model of the world that, tells you cannot walk through an obstacle and you have to go through the door because you can't walk through a wall, right? And you can't just snap your fingers and disappear. So, so your model of the world tells you what to do there, right? You have to use it as a simulation. You're learning to drive. You have a model of, you use your model of physics basically to kind of figure out like, how to drive, how you park your car without bumping into obstacles. You can use your intuitive model of geometry and the kinematics of the car. You know that if you drive near a cliff and you turn your wheel to the right, the car will veer off the cliff. And because you know about gravity, you know that the car will fall down the cliff, and you don't try because you know something bad is going to happen, right? So your model of the world like helps you learn to drive without hurting yourself. Once you've train yourself to drive a car for more than 20 hours, it becomes automatic and you don't need to think about it anymore. You don't have to use your model anymore. But in the first few hours of driving, you have to use your predictive model of how the world works. Now you're in your workshop and you're trying to build a little box out of wood. You have to kind of plan, how do I cut this thing? And, I'm going to put a screw or nails or glue or whatever, right? You have, again, a model of the world. And every new situation you face, you have to basically use your prefrontal cortex as a model of the situation you're facing. So here's what a hypothesis about what consciousness is due to the limitation of our brains. Our brain has basically a single engine to do world simulation in our frontal cortex. We only have one, okay? And we need to configure it to the situation at hand to simulate the situation that we're facing. Okay, and that's why we can only think about one thing at one time, at any one time. People call this attention, but I think it's a hardware limitation of our brain that we have only a single simulation engine, physics simulation engine in our frontal cortex, and we need to configure it to the thing at hand. The thing that configures it is consciousness. Okay, that's the thing that deliberately says, okay, I'm facing this situation and configuring my brain to attend to that situation. And I'm kind of simulating, I'm sailing and I'm simulating the airflow on the wings and the water flow on the, on the centerboard and daggerboard or whatever. I only have a single engine. So consciousness is not a feature, it's a bug. It's a limitation. It's due to a limitation of our brains.
Thank you. I'll think about it.
It's a hypothesis, right? I don't have hard evidence for this.
So Zlatko, I saw you put a comment in the chat, but maybe.
Yeah, sorry, I thought that yeah, we're gonna maybe pose the questions and so on. Very short question, Ian. Talking or thinking in terms of the analogy of energy landscape, optimal path in that landscape, Lagrangians, Hamiltonians. Has anyone in the computer science area considered the Hamilton-Jacobi equation, which is kind of a little bit specific if you represent physical system, which is used for classical physics systems, you can eliminate time out of it from certain type of problems and then maybe solve the spatial part. And is there maybe analogy or possibility to remove the training in that way if that transformation works of the computer science problem to this physics?
Okay, how would that remove the training? I missed that part.
Well, yeah, well, the problem itself, the Hamiltonian needs to be in such a way that for specific problems like planetary orbits or so, you can separate that spatial and time dependence, and then you can solve one without the other. So you can solve the spatial part, and then at the end you get the time evolution or so.
I see. Okay, interesting. Okay, so that's something I would have to explore a bit more. I mean, I'm seeing your comment, and there's some stuff that I need to read, or maybe I should talk to Yann LeCun because
It is, I think, something that, yeah, quantum loop gravity people
right.
use or try to use. Just, yeah,
I see.
Kind of.
Okay, one thing
the
that,
landscape
in that respect, there's been some work on people who are basically using recurrent neural nets as phenomenological models of physical processes, but physical processes that have symmetries in them that, for example, preserve energy, so they satisfy Hamilton-Jacobi equations and things like that. And so you build a neural net in such a way that by construction, it will satisfy Hamilton-Jacobi equations. And, and then you train basically the Hamiltonian. So that you observe a trajectory of the system you're trying to model, and you basically train the Hamiltonian so that this trajectory becomes an extremum of the Hamiltonian.
But the training part is time evolution process, is it? It is.
Yeah, I mean, you view a whole trajectory, whether it's a trajectory over time or space, right? Is a dimension. You view it as an entire trajectory, and kind of optimize the Hamiltonian, so that the observed trajectory are extrema of the Hamiltonian. There's some work by actually my colleague Léon Bottou on this. I can't remember the title of the paper. It wasn't called Hamiltonian recurrent neural net, but it's what was it called? Anyway, it escapes me right now. But there's also some work from DeepMind on the same topic, and some work by a guy called David Duveneau. He's at University of Toronto on basically viewing neural nets as differential dynamical systems with ordinary differential equations, and in continuous time. So yeah, it's an interesting connection. Yeah, absolutely.
Thanks.
So are there any other comments?
Can I have a question? Hi, Professor Jeffy. Hi, Professor.
Hi.
Okay. I just don't know because it's very similar to you have some statistical model and then you find a low energy point of that. So I think, can you use this machine learning to find the ground state of many-body system in condensed matter physics? I think that could be some similarity or something.
Well, so that's a bit what people are doing. Yeah, I mean, that's an interesting question. So there's a whole area of machine learning called amortized inference. Okay, this sounds strange, but basically it comes down to training a neural net of some kind to predict an approximate solution of an optimization problem. Okay. So let's say you have, some complex optimization problem that, may require, your problem may be NP complete or may require a complex algorithm to solve it. And what you'd like is an accelerated way of giving you an approximate solution to it. Or maybe the problem you're trying to solve is, solving PDEs like Navier-Stokes equation or something, which involves several steps, some of which are computationally a little difficult. So what you do is you train a neural net to essentially give you an approximation to the solution of the optimization problem or the whatever problem you're trying to solve. And this works surprisingly well. It seems like, it feels like a free lunch, because why would it be that training a neural net to solve an optimization problem would be more efficient than actually solving the optimization problem in the first place? And the answer to this is probably that the problems you're trying to solve are usually very structured, and the general solutions to those problems with optimization do not exploit the structure. So machine learning system will exploit it. It will, so that's the, that's something that's kind of connected to the question you're asking. I think it's a quickly growing field of training neural nets to kind of give approximate solutions to difficult computational problems, or problems in physics or energy minima. So people are doing exactly what you're talking about. I apologize for the background noise. In the context of molecular dynamics, so protein folding, for example, right? So the most successful methods now to predict the conformation of a protein are based on deep learning.
So do you have a collaboration with DeepMind?
Well, it's a little difficult because, you know, I have friends at DeepMind. I have former students and former postdocs at DeepMind. We talk all the time. We, you know, read each other's paper, and, you know, we produce some of our results. But there's a little bit of a rivalry between Facebook, AI Research, and DeepMind. So there's no real collaboration, I would say. But you know, it's you know, friendly competition, I would say.
So, a related question. You mentioned that in principle we can try to let robots develop some kind of common sense by watching a lot of videos. And there is a very good data set of videos that we have, which is YouTube. Are you aware of any experiments of that scale that utilize this data set?
Okay, there's a lot of experiments of people trying to use video prediction to train a neural net to basically understand the world or to represent images or for robotics applications. So there's a group at Berkeley, Sergey Levin, Peter Abil, another group at Stanford, actually Chelsea Finn, who is a former student of the above. There's a lot of people working on what's called model-based reinforcement learning, which is kind of the form of reinforcement learning for robots that use those predictive word models. There's a lot of people at Facebook and DeepMind that try to do this. Here's the main thing, though. The main problem is that we don't actually have good methods to learn from video, to learn good representations from video. They don't work that well at the moment. There's a lot of work on it. It just doesn't. It's not very successful until. So there's a lot of hope that methods like Barlow twins, like VicReg, which is very new, I didn't get a chance to talk about, you know, would be kind of methods that would allow us to do what you said. You know, just plug a machine to watch YouTube all days and see what comes out. Currently, the methods we have are not good enough for that.
If I may ask, earlier you said that you know, fill in the blank type tasks were very successful in pre-training a lot of different models. I was curious if you felt that there was something special about these tasks that made them so effective, or is it just that they're cheap to make and get examples for?
Well, I think to some extent, you know, the essence of intelligence is the ability to predict. So you would expect that, you know, being able to predict what's going to happen, or you know, filling missing information is really kind of the essence of what constitutes intelligence, right? Humans do this much better than most animals in most situations, not every situation. But like, for example, again, if you train yourself to predict what the world is going to look like when you move your head 20 centimeters to the left, the simplest explanation for this is that every point in the world has a depth, right? And so the notion that the world is three-dimensional would emerge naturally from the fact that you see the world from multiple viewpoints, starting with your two eyes, actually. Then once you have that, you know, you move your head, and objects that are nearer to you than the background move differently. So you have occlusion edges. And now the notion of object, of things that move together, basically, emerges naturally. So the fact that there are occlusions, that there are objects separated from the background occurs, you know, emerges naturally from this. Then you realize that, you know, when you move your head a little bit, an object will disappear behind another one, but reappear on the other side. And so object permanence also, you know, occurs naturally. So you could think of like a whole hierarchy of concepts that would naturally emerge from training yourself to predict what the world is going to look like in a second, in a minute, in an hour. And that would be sort of, you know, if you don't act in the world, then that would be sort of a passive model of the world. But if you allow yourself to act in the world, then it would be a causal model, because now you know that your action actually had this effect, right? And that's kind of also an essential piece of intelligence, which is, you know, establishing causal relationships. Humans are actually not very good at causal inference, contrary to what you hear. yeah, that's why I think, those idea of training by to fill the blanks is really kind of a good basis.
So are there any other comments? If not, I'd like to thank you, Yann, for a really interesting introduction to a very fast developing field. And we look forward to hearing many of the outcomes in the near future. So thank you very much. And we would like to continue this discussion and hope to have some more interaction, and maybe you come back at a later stage.
Yeah, that'd be with pleasure. So thank you so much for inviting me. I really apologize for the background noise. I think my neighbor is mowing his lawn or something. And it was a real pleasure. And thank you for the reference from Zlako. I'll look at some of that stuff. Thank you so much.
Yeah. Bye-bye. See you next
Bye-bye.
week. Bye-bye.
Twister?